Right, well, it's great to be here, and it's a little bit of a weird occasion for me. If you don't know, Pat was my dissertation supervisor, and I'm looking around the room, and there are some of my former teachers here, so I hope we get a good grade for the lecture. I'm going to talk today about a paper that Pat published exactly 50 years ago, 1962. It's an absolutely terrific paper. In my view, it's one of the great classics of 20th century philosophy of science. And I want to just briefly tell you what the core themes of Pat's paper were, and then transfer that to a contemporary example to see how you can apply this to some issues that are important in philosophy of science today. So here's some of the main themes of the 62 paper. One of the essential features that Pat was emphasizing was that in order to get from high-level abstract theory down to the data, you have to interpolate a hierarchy of models. And some of those are going to be of different logical types. Second thing there, which in fact was picked up later by Bogan and Woodward, that there are theoretical notions in the theory which don't have any direct observable analog in the experimental data. That means that the mapping from the models to the data is going to be complicated. The third point is the really important one, in that models of the data are selected from possible realizations of the data on the basis that the theory of the experiment tells you what constraints there have to be on the data in order for them to be models of the data. Now, I'm going to generalize this a little bit because I want to focus on some issues that are outside traditional experiments involving computerized instruments. I'm also interested in simulation, so I'm going to talk about models of data generating conditions. Now, there's an ongoing issue in philosophy of science about the relationship between experiments on the one hand and simulations on the other. One way to approach this, which I find fruitful, is to ask oneself what the epistemic differences are between the data that you get from traditional laboratory experiments and the kind of data that are cranked out by simulations. It's obviously, at least I think it's obviously, that there's going to be a difference, but one's got to articulate that, and it turns out not to be so easy. The second question here is to ask what the nature of the relations are between the models of the data that Pat was talking about and the actual concrete data that you're getting from the experiment. And the third question is, once you've got answers to those, what does that say about the nature of biodynamics? And we're going to walk through some stuff and then we'll come back to these questions. Here's the running example that Pat used in the paper. It's beautifully simple and illustrates the points in a very transparent way. For our purposes, the thing to focus on here is that theoretical parameter theta, that's the learning parameter. And one of the things that one is trying to do in these situations is to provide an estimate of the value of theta. Now, here's one of the things that Pat did that I thought was really insightful and people have not properly appreciated. When people are talking about models of data, they tend to think that we're going from the top down. What Pat said is that frequently what you're doing is you're starting with the data, and what you want to do is to find some kind of learning theory and evaluate the parameter that's going to appropriately represent it. And the focus of Pat's own paper was on the statistical methods that you use, the statistical models that you're using to appraise the data and see which of those data streams actually count as models of the data. Now, again, I'm going to generalize. I'm going to go to a different context. That's context of instruments that use computed tomography. Now, you're all familiar with these from medical context, but I want to emphasize that these methods are very widely used. They're used in radio astronomy, they're used in ground sending radar, and a lot of other areas. And if we think about the images that they produce, you can think about that as a function that's justified in the plane, and the value at some point in that plane represents the value of some property possessed by the target. So the analog between Pat's theta and these things is that what you're trying to do is to estimate the values of G. And the second parallel is when Pat was saying that what you often do is you go upwards from the data to the value of theta. In these cases, what you're doing is using a very sophisticated set of methods of inverse inference to get from the data to construct the image. So you're actually going backwards from the data up to the feature. And here, in general, we're going to focus on the property of interest being the X-ray attenuation coefficient. And here's just a bare rudiments of what's going on. So you're looking at a slice through a target, slice through the body, something like this, a two-dimensional situation here. Here's the target. One side you've got an array of M emitters of X-rays, and on the other side of the target you've got a corresponding set of M detectors. The X-rays are emitting, sources are emitting the X-rays of the known intensity as they traverse the target, and the target has differing densities according to different kinds of tissues. They will be differentially attenuated, and the values of the resulting intensities will be picked up on those detectors. The whole apparatus here is rotated then through an increment of theta. The target stays where it is. You get a different set of projections for the next value of theta. And so you end up with rotating the detectors and the emitters through pi degrees. And the data that you get then is an m by n matrix, m being the number of detectors and n being the number of values of theta through which you've rotated the apparatus. So that's the basic setup, and the task is to reconstruct the interior constitution of that two-dimensional slice. All right. Here's the mathematical techniques, and this is corresponding to that high-level learning theory case that Pat was giving you. So this is at the top of the hierarchy. What you've got here is the projections at the value along the detector framework of R at given value of theta. And you get that by picking out that value of R by using the delta function. Here is the target frame value for the attenuations. And what you're doing there is simply accumulating all the values of the attenuation along the ray that corresponds to the value R that's picked out by the delta function. And that's the radon transform of G over the projection.